So, in our previous lectures, we went over bondings in organic molecules. You should know that organic molecules, they are not as flat as we draw it on paper. They have wedges and dashes when you draw it. And they have those kind of like zigzag conformation when you actually build a molecule. So today, we'll be looking at the actual conformations of these molecules and see like how to understand rotation of single bonds in organic chemistry. So are we ready to get started? In general, when we talk about organic molecules, you should recognize that in reality, rotation of these single bonds, like this is an ethane just with different colored hydrogen. The rotation of all these single bonds, or even like this kind of rotation, it's happening all the time at room temperature. Because these bonds will be able to rotate throughout, to form different kind of conformations. So in this case, let's look at ethane as an example and to analyze it a little bit more carefully to see that how does different conformation of ethane come to play when we say organic chemistry. So if you have your molecular kit of ethane, wonderful, take it out. And if you don't, we can look at my document camera together. So the first concept we will introduce is two different kind of drawing of the 3D conformation of your molecule. All right, it will come to more play later on. So first one, you're already pretty familiar with, which is the wedges and dashes. So for each carbon atom, you draw two single bonds that's like in plane with each other. Like in this case, if I'm considering my plane being defined by my black hydrogen, my carbon, my black hydrogen. So that's where I come from. So these are my black hydrogen, my carbon, and the white hydrogen. So these four atoms define my surface, my plane of drawing. All right. And then we have two of my blue hydrogen pointing out towards you. So in this drawing, these two blue hydrogen will be the one that wedges out. And at the same time, you'll have two red hydrogen that dash in. So that's a normal wedge and dash drawing of my ethane molecule. So far, so good? This is a little bit hard to picture without the molecular kit. And it's a little bit hard to justify like how far away my atoms are. So that's why we want to introduce a different kind of drawing called Newman projection. So the Newman projection is looking through this chemical bond. So we're looking through this carbon-carbon chemical bond here. So I'm going to change the viewpoint to here. Like looking through the carbon-carbon bond. Now, this is the flat region that's on the paper. And now we're just rotating it. If you have one with you, you can also rotate it yourself to look through the carbon-carbon bonds. And that's my eye. So how do we draw these Newman projections? On the left-hand side, let's think about it this way. What do we have here? We have a carbon on the top, and then we have a carbon that is on the bottom. So in this kind of drawing, like what we do is you first draw a circle. Let me put it the right way. So first you draw a circle. Now in the center of this circle, that's your carbon atom right here. All right, or that's your front carbon. Now in this front carbon, you can imagine you have one hydrogen coming out. Okay, so you have like one hydrogen coming out like that to the top, and then the other two coming out this way. All right, so using my color coding, all of them are hydrogen. So the top one will be a blue one. This one will be a red one, and this one will be a white one. Likewise, for the carbon on the back, you can draw the same kind of three hydrogens coming out to each other. So the red one will be here. And you have the blue one on the right, and then the gray one on the left. All right. So this is one quick introduction into what is Newman projection. Newman projection is effectively just a different way of looking at the same molecule. But it gives you, yes?
I don't know if I'm just seeing it wrong, but are there three reds?
One of them should be blue, actually. Which one? This one. This one should be blue. Yes. Thank you. All right, so Newman projection is effectively a different way of drawing your molecules, so it's easier for you to see how distant or how close my hydrogen atoms are around a single bond. So this kind of conformation, like if you look at the dihedral angle, we're talking about the distance here. These are called staggered. And this is considered to be the more stable conformation of my ethane. So all my hydrogens are staggered with each other. They're not directly on top of each other. All right. But as we were saying, single bonds can undergo free rotation. So what if we rotate the top bond by like 60 degrees? And you end up getting your hydrogen atom directly on top of each other. So if we put that conformation to the normal viewpoint, what we see is now you have, if I have like my blue hydrogen defining the plane with my carbon atom, so I'll have to draw this a little bit differently. So I have my blue hydrogens defining my plane with my carbon atom. So in the drawing, I'm using like solid line to define my surface or my plane. And then we have two hydrogens wedged out from each other. So in this case, it's the white and the red. And then you have two more that's dashed away from the plane that we defined. Right. And then, what does that look like if we put it in the Newman projection? Well, so that's on top of each other. Or it's the same way, right? When we're drawing that circles, we start from the circle. So that's my front carbon. Let's say we're looking through this bond again. And in my front carbon, we have a blue one on top. And then we have a gray one and a red one. And now my hydrogens are directly on top of each other. So we have hydrogen, hydrogen, hydrogen. So the blue is on top of blue. The white is on top of red. And your red is on top of a white. So this is called the eclipsed conformation, meaning this bond is less stable. When we say it is eclipsed, we're saying my hydrogen atoms are directly on top of each other in the Newman projection. They're less stable. And to be more specific, when we say the eclipse conformation is less stable, this conformation is about 2.9 kilocalorie per mole higher in energy comparing to the staggered conformation due to a torsional strain. And in organic chemistry, I mean, if we look at ethane, this is the more like, I guess, the standard symmetric molecule, we only have hydrogens in place. So we can write out the entire potential energy diagram of ethene rotation. So what does that mean? It means like if we start from this kind of diagram, we start from a favored staggered conformation that is more stable, we can continuously rotating throughout that single bond so that we're getting a potential energy surface. So what is a potential energy surface? On the y-axis, that's a energy, or the other way to put it, that's the some kind of electronic energy telling us how stable a conformation is. And later on, we can also have a y-axis. The y-axis is energy. On the x-axis, we have our torsional angle. So that's a dihedral angle between your hydrogen-carbon, carbon-hydrogen bond. So in this case, what are we looking at? So I'm just going to rotate my molecule with you. I think I built it a little bit differently, so I'm just changing the molecules so that it fits the drawing on the figure. So let's do this. I'm going to give each of my points on here a label, A, B, C, D, E, F, and G. So I'll do a quick exercise. I'll rotate this chemical bond randomly, and you will tell me which point is that conformation and how stable is that conformation. All right, ready to get started? So let me put it this way. This one. Okay, quickly. Tell me if it's eclipsed or staggered. Raise your hand if you think it's eclipsed. Okay, so we get it right. Right, so eclipse, you have hydrogen on top of a hydrogen. And which point it is, if we're looking at the coloring? Do we have one here? Okay, so that is A, B, C, or B, D, or F. So B, D, F. Okay, raise your hand if you think it's B. D, yes, all right, so that's how far we should go. And also, like, what do I expect you to know? Well, we give you this kind of drawing, and now I can just remove one of these conformations and say, like, can you put it in? Right, so imagine how you're rotating it and then putting the drawing of that conformation there. And for the staggered, we can do the same thing. Now, what about this one? This one is now a staggered conformation. And which point it is? A, C, E, and G. Anyone? Yeah, so this one is my E, right? So we have the gray one, the red one, and the blue one. So far, so good? It's just essay, like it's. Can you explain that part? This one? So first of all, you identify this one to be the more stable staggered conformation. And then within the staggered conformation, you're thinking, okay, which one is on the top? You have the white one on the top, and then here you have the red and the blue one on the bottom. Okay, this looks so far so good, very straightforward. But things can get more complicated when you get more substitution on your group. So now if we move around, yes?
So you rotate clockwise when you're doing...
It doesn't matter how you rotate it, you'll eventually get back to the same position that you start from.
But if you're drawing a diagram, it doesn't matter if you do it clockwise or counterclockwise?
No, it doesn't matter. Like, basically that diagram, you'll continue going until you reach to the end point. Okay, but things can get more complicated. So now imagine I'm replacing one of my hydrogen with a sterically Bartier group or a methyl group. Okay, so we're just looking at one more carbon in my molecule. So we're looking at propene for now. So I'm just going to organize it. So now what we have, looking at propane, when we draw it out in my wedge and dash conformation, right? So you have your methyl group, carbon, carbon, and hydrogen. So my methyl, carbon, carbon, hydrogen defining my plane. And then you have a red hydrogen wedge out, a blue hydrogen wedge out on the other carbon, and then a blue one dashed in and a red one dashed in. So far so good. Now, can we come up with the Newman projection of this specific wedge and dash drawing? If we were to come up with a Newman projection, what does it look like? Okay, so you flip it. You have a model with you, you flip it, and you observe what it looks like. Right, so it's the same idea. You start by drawing the carbon on the top. It doesn't matter which one you put in the top, both are correct. I just randomly pick the one next to my methyl group on the top. I have my methyl group on here. That's my CH3. You have a red hydrogen and a blue hydrogen. And then on the bottom, we have a white hydrogen, we have a blue hydrogen, and a red hydrogen. All right. So, yes.
Will we be allowed molecular kits during the exam?
Yeah, you can bring your molecular kit, yes.
How do we know if it's wedged or dashed, and the difference between that and normal bond?
So first of all, it doesn't matter which one you put as wedge and dash. So in this molecule, we could easily redefine. I can define my molecule as like hydrogen, carbon, carbon, hydrogen, right? So I can draw it in a different way. So that is my carbon, carbon, hydrogen, hydrogen, and then I wedge out my methyl group, and then my dash my other hydrogen. Same applies, like I wedge out my red hydrogen and dash my other hydrogen. So it doesn't matter how you draw it as long as it is the same molecule. And also like this one is the same, right? If you do the other viewpoint, you can draw your Newman projection differently, but they're the same Newman projection. They're all correct. Yes?
You said that you can do either the Newman projection this way or the other way, but if in like the problem they say the viewpoint is from this angle.
Mm-hmm. Then you have to specific. Like in this one, if I specify like the viewpoint is here, then this carbon will be my top carbon, and you have to look at this way. Or I mean, but if you rotate it, like you draw it like this, that's also correct. All right. And likewise, like in ethane, when we're looking at propane, you can also have the less stable eclipsed conformation. So that is, if we draw it this way, well, if I rotate my single bond by 60 degrees, so now my methyl group is directly on top of a blue hydrogen, as we were drawing here. And now this is a eclipse, less stable conformation, which is higher in energy by about 3 kcal per mole. So, yes.
So why is having the version important? Like, what is that? What does that do?
Sorry, I can't hear you.
What does the Eclipse version do for us? Like, what do we use that to do?
So in this case, it's just recognizing the fact that eclipse conformation is higher in energy. It will later on come to play, especially when we're explaining selectivity or reactivity when looking at the molecule. And just as a fun fact, I'm using these kind of rotational barrier potential energy surface in my research right now. So people still use it to explain like the conformation of molecules. And things can become more complicated when we look at a even more larger molecule, which is butane. So we're gonna do the same kind of analysis for butane. Now we have, it's butane, so 4 carbon. And in this case, we're doing the same thing. Well, actually I should do it this way. Well, my red and blue are reversed. Okay. I have to redo it. Okay, so I define my pen as methyl, carbon, carbon, and methyl. And then my blue hydrogen is wedged out. My red hydrogen is dashed in. And now the other carbon, my red hydrogen is wedged out. Blue hydrogen dashed in. Okay? Now, thinking about the rotational profile for butane, we now have a much more complicated scenario because your methyl group is significantly larger comparing to your hydrogen. All right, so let's do this. I'm just gonna keep this one here, and then we'll do the energy profile together on paper. So let's see where we start. We'll start from the lowest energy conformation. So remember when we're doing the energy profile, we have energy, and on the x-axis, we have our torsional angle. So in here, when we're looking at it, what is the lowest energy conformation? So if we're looking through the center carbon-carbon bond, that is this way, right? So you want to put your sterically bulky group as far away from each other as possible. So what does that mean? In this case, we're looking through the center carbon-carbon bond, and I want to put my methyl group and my methyl group far away from each other. So that means on the diagram, on my lowest energy point, we can have a Newman projection of my methyl group. That's the one pointing up, my hydrogen, and hydrogen. And on the bottom, we have my CH3, hydrogen, hydrogen. So this is called the anti-configuration. And when we say this is anti, we're saying the sterically bulky group are as far away from each other as possible. They're staggered, and at the same time, they're anti. So staggered defines like we have like a 60-degree dihedral angle in between. And then anti describes your methyl and methyl group are as far away from each other as possible. All right. And now, what if we rotate 60 degrees? So now my methyl group is on top of a hydrogen, and this methyl group is also like right below a hydrogen. So we get to the unfavored eclipse conformation because your methyl group and hydrogen are right on top of each other. So how to draw that out? Well, we draw it on the higher energy point. You have we rotate it, so we have a hydrogen, CH3, hydrogen, and on the bottom we have a hydrogen right under the methyl. You have a methyl right under the hydrogen, and then you have a hydrogen right on top of the hydrogen. So its eclipse is less stable. All right. And now, taking one more rotation of 60 degrees, we get it to here. Let's draw the Newman projection first. We get the methyl group is now here, and hydrogen. And on the bottom, we have CH3, hydrogen, and hydrogen. So note that I'm keeping the bottom one unchanged. You can also rotate the bottom one. It doesn't matter which one you rotate. Also doesn't matter which direction you rotate. But if you compare this conformation, this is also a staggered conformation. But if you think about this staggered conformation, Comparing that to my anti-conformation, which one is more stable? Now my methyl group are neighboring to each other. They're not eclipsed to each other, but they're close to each other comparing to the anti-configuration. So this one is called the gauche configuration. So it's going to be higher in energy comparing to my anti-configuration because my methyl group and methyl group are closer to each other. I sometimes use this kind of label to indicate there is steric repulsion between the methyl group. All right. And now it's the same idea. I'm rotating my single bond again. So now my methyl group and methyl group are right on top of each other. So we can draw it out as, well, my methyl group and my methyl group are right on top of each other. So this one is my highest energy eclipse conformation. Because my methyl group and methyl group are even closer to each other in this molecule. Right? They're right on top of each other. Like if I'm rotating my methyl group, I'm actually going to bump in to the bottom methyl group. And if you have your molecular kit, you'll also see that it's actually bumping in to the methyl group. So they're super close to each other. That's my highest energy conformation. All right. And we can keep rotating to get it to this part. And that goes down to my gauche conformation again. And in here, this gauche conformation, the staggered conformation, will have the same energy as the previous one. They're effectively the same energy. They're the same kind of interaction. And rotating it another 60 degrees, we get it to the top eclipse conformation. Am I rotating too much? Okay. And doing it another rotation, we're getting back to our original anti-configuration. All right. And I have a better drawing on my iPad here. It's the same kind of drawing. You'll also see that in the annotated notes. Like what we were saying on this rotational profile is we start from the lowest energy anti-configuration. Your two methyl groups are as far away from each other as possible. So that's our most favored or lowest energy staggered conformation. And in the middle, we have our gauche conformation. So your methyl group are not directly eclipsing on each other. They're still staggered, but they're closer to each other as compared to our anti-configuration. So this diagram, I'm rotating the bottom one, so it's a little bit different. And we have two gauche conformation. And on the top, we'll have three eclipse conformation. So the methyl on top of methyl is the largest proportion and highest energy. Okay, I'll take any questions you may have, because you guys have been very quiet today, and that worries me. I'll take as many questions as you have before we move on. Yes?
Are the bottom two both gauche?
Right, so the two blue ones are both gauche. So when we say they are gauche to each other, we're saying they are staggered. So it's like still 60 degrees. But the methyl group are neighboring to each other. They're not anti to each other. Yes?
Is there an order of stability for the eclipse?
Right, for the eclipse, we also have an order of stability. You see, like that's why we draw it here, right? So the methyl group on top of methyl group, these are the largest energy, and these, the methyl on top of hydrogen are slightly lower in energy, but still pretty high. If you want a number, we actually can calculate these number using quantum mechanical calculation. Like if we put our NT to be like 0.00, my gauche conformation will be about 0.9 kilocal per mole. And then my more stable eclipse conformation will be 3.6. And my highest energy eclipse conformation will be about 4.0. Yes?
Is there a special name for the metal eclipse on top of the metal, or is it just like?
You mean this one?
Yeah.
There should be. I don't have it on the top of my head, and I don't expect you to know about it. Yes?
So you said that the conformational changes are kind of always happening. Does it spend like a higher percentage of the time in the most stable one?
Right. So here's the thing. When we're talking about the rotation is happening, as a matter of fact, it depends on how much energy is required for that rotation to take place. So if we're looking at room temperature, normally like anything within like 10 kilocal per mole window can take place. So that's why like carbon-carbon rotation is able to take place at room temperature, because even if we're going from like NT all the way to the highest energy one, it only takes like 4 kilocal per mole. But if we're looking at population, then most of my molecule will be in the lowest energy NT conformation, but they can interconvert with each other. We'll go over that thermodynamics hopefully sometime later this quarter. Yes?
Considering if like we had to draw the lowest and highest energy like chart conformations in terms of like Newton projections, we correspond like the staggered formation for the lowest energy chart conformation and the eclipse for the highest.
First of all, chair conformation is something different. We will talk about that in cyclohexene. This one is the Newman projection. So when we're drawing the Newman projection, actually let's look at one example together, shall we? So here's one example. Can you draw the lowest and highest energy conformer of this molecule, which is 1, 2, 3, 4, it's 2-methylbutane. And we'll specify what is our viewpoint. So let's say we're looking through this bond. That's mine. And we can view the molecule together. And let's see. Well, I need another methyl group. So let me find it out. If you have one, we can view that together. Okay, so in here, what do we have? So this is the molecule that we just built. We want to put the 4 carbons, basically, the 4 carbons define my plan. And we're looking through the chemical bond of my center carbon-carbon bond. And what does that give us? It gives us this kind of group. All right, so when we're looking at the lowest and highest energy conformers, you have to think about it. The lowest energy conformer must be some kind of like non-eclipse staggered conformation. And your highest energy conformer will always be a eclipse conformation. So in this case, how do we draw it? We first draw a staggered conformation. So on the top, we want my methyl group to be as far away from each other as possible. So in this case, we have my H3C and my HCH3 and my hydrogen. So that's the top one. I'm just gonna keep my top one drawn and not changed. And now I'm thinking about my bottom one. How can I rotate my bottom one so my bottom methyl group is as far away from my methyl group as possible, remaining a staggered conformation? So there are 2 different things that can happen. You can have the bottom one in between a carbon and hydrogen, or you can have the bottom carbon in between two methyl group. Right, so this one is a higher energy staggered conformation. Alternatively, this one will be the lower energy staggered conformation. So it's more like you have a molecule in your head, you start to rotate that hypothetical single bond. And when we're drawing this out, we'll end up getting a methyl group here, and hydrogen, and hydrogen. Right, so that's our lowest energy staggered. Yes?
It doesn't matter which side you have.
No, it doesn't matter. I mean, it's the same, right, if I draw it here. And on the potential energy surface, it'll have the same energy. In both cases, if you count it, you can say, okay, we have one CH3 gauche, two CH3, and that's it. And, well, what about the highest energy conformation? The highest energy conformation, you will have the methyl group directly on top of another methyl group. So for highest energy conformation, we know it must be an eclipse conformation. So in this case, we'll have a methyl group, and methyl group, and then a hydrogen. Directly on the bottom of my methyl group, we have a CH3. And on there, we have hydrogen and hydrogen. And this is my highest energy. Just out of fun, we can also draw the second lowest and the second highest. So in general, we have 4 different conformations we can come up with in this 2-methyl butane. And what about the second lowest staggered? So the second lowest staggered would be, well, I'm keeping my methyl group unchanged. It's staggered, but I have my methyl goes to 2 different methyl. Right, so this is my second lowest. We have the methyl group goes to 2 methyl. And we have another eclipse conformation that's lower than the one we just draw. That is, you can put the hydrogen on top of your methyl group. So that's, well, actually let me rotate it this way so it's befitting. So we have a hydrogen and a methyl, methyl. So the hydrogen is on top of a methyl group, and a methyl is on top of a hydrogen. So the third high energy. Well, so number 3. Right, so for renting the energy of these 4 Newman projections, or I can give you the 4 Newman projections, I'll ask you to rank these Newman projections based on their energy. This will be my lowest, second lowest, third, and fourth. So your eclipse is almost always higher in energy than your staggered. And then within the staggered, you count how many sterically bulky group is gauche to other steric bulky group. And within the eclipse, you count how many steric bulky group are eclipsed with other steric bulky group. Yes?
What's a steric bulky group?
So steric bulky group means it's bigger. So a methyl group is bigger than hydrogen. An acyl group is bigger than a methyl group. An isopropyl group is bigger than a methyl group as well. And the terbutyl group, meaning you have the 3 methyl attached to the same carbon, is even bigger. So it's just larger. Yes.
Oh, it's a bit of a weird question, but like, why does the diagram, like, when it goes towards the top, why does it start rounding out? Because I thought the energy would just keep increasing as the bonds get closer and closer to eclipse.
You're going back to the energy diagram?
Right, exactly. At the top starts rounding out towards like, you know, the top, but then I'm wondering why that is. Because I thought as the atoms, like, or sorry, as the groups get closer and closer, the energy doesn't like start slowing down. It just goes
Well, so the energy increase is not a linear process. It's more like this sort of smooth curve. And these are just my sketches. These are not real potential energy surfaces.
Oh, okay.
Yeah. Yes.
So is there a situation in which there's a molecule that has such multiple groups that takes priority over the whole anti versus eclipse energy thing?
So first of all, when we're looking at staggered versus eclipsed, the staggered is nearly always more stable comparing to the eclipsed. Now we always will have very extreme situation. Like for example, if I have a tributyl group that is staggered to like two different tributyl groups, maybe it is even less stable compared to the eclipse. But those are exceptions that I don't expect you to know, or I don't expect you to be able to predict. Okay, so for this part, my expectation to you is know how to draw the Newman projections from the wedge dash configuration, and also vice versa. If I give you a Newman projection, can you draw it back into the wedge dash configuration? And then for the Newman projections, know how to rank the energies of different Newman projections and know why some of them are higher energy or lowering energy. So know how to draw them and know how to predict the relative energies in these Newman projections. All right. And, well, we have about 10 minutes left, so I'm going to quickly introduce cycloalkanes. We'll not be able to go over cyclohexane so far, but let's go over the conformation of cycloalkanes first. So we went over enough discussion on these linear molecules. So far so good. They are linear molecules. They having some kind of steric restrict, but at the end of the day, they're still like pretty happy. It's linear, right? So most of the carbon will have the bond angle of 109.5 because they're tetrahedral angle. And also when we're talking about sp3 carbon, remember we were saying the bond angle between the bonds in my sp3 carbon is 109.5 degree. For my sp2 carbon, that's about 120 degree. And for my sp hybridized carbon, this is about 180 degrees Celsius. 180 degrees. But what if we're making my molecule into a ring, and then we're having some problem? I'm trying to force it 1 second. You see, like I'm trying to make this 3-member ring with my molecular kit, and I can't even do it without forcing it. And here's a problem called ring strain, right? So that's a molecule. We're talking about cyclopropane. When you make it to a cyclopropane or a 3-member ring, naturally you're expecting all 3 of these chemical bonds have the same kind of bond angle because, well, the carbon-carbon bond have the same bond length, and based on normal math, we know they must have the same bond angle, or 60 degrees. But that's a problem because our normal sp3 carbon want to have a bond angle of about 109.5 degrees. So that introduces several kinds of strain in the cyclic molecules. So in cyclopropane, for example, like what we were saying, there are 2 different kinds of strain in the cyclopropane. First one is called the angle strain. That is, my cyclopropane will have carbon-carbon bond angle to be 60 degrees instead of 109.5 degrees. So that is called an angle strain, meaning my carbon-carbon bond angle in my cyclopropane is significantly different from 109.5, where my sp3 carbon is happy. In addition to the angle strain, your cyclopropane will have a more torsional strain. So torsional strain is the one we just discussed, which comes from the eclipsing of your atoms, right? So in the ethane case, you have hydrogen directly on top of each other. So if you look at cyclohexane from the top up, we see that all the hydrogens are eclipsing over each other. And that's also because the carbon is making 4 bonds, and that's the only way the carbon can make bonds with your hydrogen. So these are my torsional strain. Or the other way to put it, like if I don't have hydrogen, I have a methyl group on my cyclopropane, then my methyl group must be eclipsing with the other substitution on the neighboring carbon. So in cyclopropane, we're expecting to have a lot of strain in that molecule. So that's why cyclopropane has been a relatively reactive molecule in organic chemistry, because itself is not stable, so the breaking of these carbon-carbon bonds will be more thermodynamically favored as we're releasing all these strain. Also, bonding in cyclopropane is very special, and we're still studying it, but nevertheless, cyclopropane is a strand molecule, yes.
So does strain equal to the energy level of the molecule?
Yes and no. So strain basically say the molecule itself have a higher energy comparing to its linear counterpart. Like if you're comparing cyclopropane with linear propane, then cyclopropane is more strain. But later on we'll see if you're comparing cyclohexane versus linear hexane, then the cyclohexane is not that strained. And we have 3D picture. So if you don't have a molecular kit, and you can find these kind of 3D visualization software online to look at the 3D structure of the molecule, that also works. Like if we look at the 3D structure of the front view, we see that you can draw the cyclohexane using the wedge and dash convention or the sketch. Or if you look at the side view of your cyclopropane, you can draw it from the Newman projection perspective. Like I'm looking through this carbon-carbon bond. So all of my hydrogens are eclipsed with each other, and my top carbon is making a bond with the bottom carbon, and that's how you draw it. All right. So today is one of those lectures that I hope you have your molecular kit with you. So you're looking at your kit with me while we're going through the way. And again, today is just an introduction into Newman projection, into how to draw these conformations. And we'll pick up next lecture talking about cyclohexane and structures of cyclohexane. And can I have my molecular kit back, by the way? Okay. That's too high. But no, I'll be outside if you have any questions for me.
Google, the campus.